Welcome everyone. In this video, we will do a review of the article Human Level Performance in Three-Dimensional Multiplayer Games with Population-Based Reinforcement Learning. First of all, we should point out that reinforcement learning is a part of machine learning, which its main feature is that learning is achieved from interaction and guidance. Reinforcement learning has shown great success in complex single-agent environments and two-player games. However, real world contains multiple agents, each learning and acting independently to cooperate and compete with each other. For this reason, the challenge carried out in this article was training agents in a multi-agent environment that combined team and competitive play. This challenge was approached by studying a team-based multiplayer three-dimensional first-person video game as it is the game Quake 3 Arena in the game mode Capture the Flag. This game is about two teams consisting of multiple individual players competing to capture each other's flags by strategically navigating, tagging, and evading opponents, and the team with the greatest number of flag captures after 5 minutes wins. The game is played on both indoor and outdoor them maps, and agents interact with the environment and with other agents only through their observations and actions. Then the aim of the author was to develop a training procedure that enables agents to acquire policies that are robust to the variability of maps, number of players, and choice of teammates and opponents. The agent's policy only receives pixels from the agent's first-person perspective and game points scored as input.
In reinforcement learning, it is the reward or reward function that defines the learning agent's objective in an uncertain environment. These rewards inform the agent how good it is to be in a particular state or game environment. A strength of this framework is that the source of such rewards is not taken into consideration, only the purely numerical feedback it receives from the environment, and so it is able to generalize. However, this is also a weakness of the system as it ignores key questions on the nature of rewards. This is what the article attempts to alleviate by giving the agents a dense internal reward function that is based on the available game points the agents may receive throughout play. Since we're wanting the agents to be particularly good at, as the game mode suggests, capturing the flag, using the result of the whole game as a reward fed to the agent is not sufficient enough feedback. An agent could learn to maximize this reward over a number of episodes without necessarily being good at capturing the flag. Therefore, we want to receive rewards at points of time when events such as capturing a flag occur. As the main motivation behind this paper is to develop a population of agents that become proficient at this game mode, distinguishing the types of rewards received would be incredibly useful. Since rewards define the immediate intrinsic desirability of environmental states, our main focus will be on values of states, which are functions of rewards that give the long-term desirability of states. The value of a state is the amount of reward an agent can expect to accumulate over the future, starting from that state and considering the states that are likely to follow and the rewards available in those states. Therefore, in this context, we want to find an optimal policy that maximizes the expected accumulative reward over a capture the flag game. To train such agents, instead of training using self-play whereby the agents play against themselves in order to find the optimal policy, which would be the optimal play of the game mode, a population of agents are trained in parallel. These agents are characterized by how they play, and so each learn how to play with a variety of different opponents and teammates. As an environment such as Quake 3 is highly non-stationary, this adds a level of complexity to the neural network used in the architecture of the learning agent. Such neural networks need to be tuned with respect to the network parameters which have an effect on the learning process. If the environment the agent interacts with is highly complex and non-stationary, the parameters of the network effectively become non-stationary themselves. Therefore, we need a computationally efficient process for probing the search space of the parameters. The paper makes use of population-based training to achieve this, which extends parallel search and sequential optimization methods.
Okay, in order to assess how the agents performed, a large tournament was formed. So in this tournament, there's an environment where the maps were procedurally generated. So every time an agent enters the map, uh, it's he is in a completely new environment. So there are three types of agents we use for the assessment in the environment. The first type is the FTW agent. The second type is the Quick 3 arena scripted bots of various levels. And the last one are human participants with first person video game experience. In this review of the paper, we'll mainly discuss the an ablated version of the FTW agent as well as human participants used in the tournament. Here is just a short demonstration of how the reinforcement learning algorithm works in practice. This is an example of the indoor procedural map as discussed earlier. Here you can see agents tagging one another and being reset and starting the game again. That's an example of the outdoor procedural map with similar concepts. Um, you can also see the agents tagging one another and resetting and going on and on. One of the key differences between the outdoor map and indoor map, as you can probably see from the map overview, is that the indoor map has a lot more walls, so that makes like an interesting dynamic in how the agent maps your movement. So moving on, we'll talk about the tournament results and how they performed during the times the agents were trained during the tournament. So as can be seen from from graph B, the agents performed a lot better during their time learning in the environment. They won most of the games, and whenever the agent was in a in a map where they had never seen the map before and they've never collaborated with other agents in the map before, the agent performed a lot better than the humans did. This situation is called zero-shot generalization. So the agents won in most scenarios. The only time humans actually had a shot of winning was when agents and humans were paired up in the same team and collaborated together. This actually shows how agents are capable of interacting and adapting to situations where their teammates are not predictable. So when humans were paired up with the agents, they had a 5% probability of winning. And after 12 hours of practice, humans were capable of about 25% of winning. There are various things to consider about performance measurement like this. There are various factors that affect the data. One of them is the performance and the reaction times of both the agents and the human participants. For example, the human participants were far likely to tag a target from a long distance because the agents are not capable of locating targets that far. However, the agents were far better at tagging targets in close range. The agents have better um, shot accuracy or tagging accuracy and a lot better reaction time. So this affected the win rate for both the agents and the human players. In order to make the data more realistic, the paper actually reduced the reaction time and the accuracy of the agents to match the human players. So when this was done, the humans had a 30% win rate against the agents. So the agents were still far better than the humans, even considering the efficiency of the agents.
So this part we will analyze. We will do the agent analysis to investigate agents that have learned a rich representation of the game. They extract ground truth state in terms of 200 binary feature at each point for game agents such as: do I have a flat? Will I be in the opponent base soon? Or did I see my teammate recently? In the case where the user has no explicitly training agent to model, they find that the FTW agents can encode features related to the past particularly well. This result shows the concept emerged spontaneously purely through reinforcement learning training. To append the visualization of agent knowledge represent, the author used T-distributed statistics neighbor embedding to reduce dimension. The figure is the result after reducing the dimension where the different color area represent different cluster. It shows that its internal state will be clustered according to the combination of high-level game state function and single neural code directly. This cluster will achieve agents to encode the different types of new functions or associate with all functions. In example, it shows the impact of reinforcement learning on the way of agent thinking. In the case where the map is randomized generated, the author let the agent play about 450,000 games. In this processing, they found that the temporarily extinct reinforcement learning made FTW agents learn how to use the memory recall pattern to find the position and also learned a coordination strategy in the process. This knowledge led them more efficient flat capturing. In the second picture, it shows some other rules that the agent can group short gameplay sequences into behavior cluster and discover or abandon some behavior at midway through training. Also, as the amount of knowledge increases, agent will be able to defeat more powerful enemies and coordinate multiply teamwork behavior. This behavior will more prominent later in training. So, in conclusion, this article, the author used a multiplayer first-person video game to demonstrate that agents can learn highly competitive gaming in a multi-agent environment. Its achievement is mainly based populational-based training and temporary hierarchical reinforcement learning with optimization internal reward. This method also used the minimus assumption to the game structure, and this represents that it could be learning in variety of multi-agent systems. In addition, its technology can also let agents emerge some surprising and complex higher-level behavior when it's trained in a rich multi-agent world. The limitation of this technology lies in the framework of the agent, which can be solved in the future.
Thank you for your attention. This is the end of our review.